Welcome to this particular module. In this module, I will be talking about uh, uh, a very important problem related to heart, and that is called atrial fibrillation. Now, generally when you see the heart pumps uniformly, that uniform pumping of heart is because of the synchronized electrical signals, but in certain cases the electrical signal starts misbehaving, and in that case either the heart starts pumping very heavily, which we call arrhythmia, or it starts pumping unevenly or beating unevenly, that is because of the misfiring of signal, and that is called atrial fibrillation. Alright. So, if you understand the how the heart, we generally learn in biology, right, that what is anatomy of heart. Just to recall quickly before we move to that problem, we will show you the, or I will show you the heart, the schematic of that, and then what is actual problem, which is atrial fibrillation, in a very short video about 3 minutes, and then what are the different ways to cure this particular problem, and where are the gaps that we can fill with the help of designing an interesting or innovative sensors. So, that is a complete idea. So, if you see the screen, you will see that the this is something which is we are being taught from long time. Heart as a aorta, and you cannot we cannot teach something else, because this is how heart is. We have pulmonary veins, left atrium, right ventricle, left ventricle, 4 chambers, as you know, right. Inferior vena cava, pulmonary trunk, superior vena cava, and then this is just basic things. There is a fiber of His and lot of other things which we are not getting into detail. If I play this video, it is just like how the heart beats, but I will show it to you in detail about that video. If you move to the next topic, which is the smart catheters, this is what we are interested in fabricating. Okay, smart catheters. Now, let me tell you what exactly the catheter means first, and then what is smart means. But before we understand smart catheters or catheter itself, we need to understand what exactly the problem with the in this particular case. So, heart diseases are increasing day by day, as you know. Recent studies says that disturbance occurring in a large population of world population, and if untreated would result in a life shortening. There is a need for accurate and affordable treatment techniques to ensure health quality. Right now, we are talking about AFib or atrial fibrillation, which is a heart arrhythmia in which abnormal electrical signals begin in the atria of the heart. This is due to abnormal conduction of electrical signals. Right, you can see here, if you see this ECG waveform, then in this particular circle you will see there is sudden heartbeat, that is QRS waves, right. So, why there are two very closely spaced ECG signals compared to how it should be like this? This is because of the misfiring of signal. Okay. So, if I come to how consequences of AFib, or what are the difficulties that may arise, is that remodeling of heart tissue will occur, and then there can be stroke due to blood clot because of this uneven beating of heart, and that blood clot can go anywhere including the brain and can cause stroke. So, the way to treat this is mostly with medications. However, right medications and combination is a very challenging process. Like any other medication, screening is very important problem, how to screen a particular drug, and we will be quickly looking at that particular problem as well. And when you talk about treating it, then what happens is that the surgeon will insert a catheter and will ablate the tissue. Now, we will talk about this after a video, so that whatever I am talking you will get it. So, let me play the video.
Depending on activity level, the heart beats about 60 to 100 times per minute. It may be higher during exercise or lower at rest. A normal heart rate and rhythm ensures the delivery of oxygen-rich blood to all of the body's organs, such as the brain and lungs. A group of cells in the heart called the cardiac conduction system, uses electrical impulses to control the speed and rhythm of each heartbeat. An abnormal heart rate or rhythm, called an arrhythmia, occurs when there's a problem with the heart's conduction system. Tachycardia is a type of arrhythmia where the heart beats too fast. Fibrillation is a type of arrhythmia where the heart beats irregularly and may be too fast. For certain types of arrhythmias, a catheter ablation procedure may be necessary to stop the heart tissue from causing the arrhythmia. After numbing a small area in the groin with a needle, the doctor will insert a short hollow tube called a catheter sheath into the femoral vein. Next, a long flexible tube called a catheter will be inserted through the sheath. The doctor will guide the catheter to the heart through a blood vessel that goes to the heart, called the inferior vena cava. The location and progress of the catheter will be monitored. When the catheter reaches the heart, the doctor will guide it to the area that is causing the arrhythmia. The doctor will find the problem areas using a 3D map of the electrical activity of the patient's heart. The tip of the catheter will emit either hot energy or cold energy to ablate the tissue in this area. Ablation makes the treated area stop working. For an atrial arrhythmia, a doctor will ablate the atrial tissue causing it. If the affected tissues are small, well-defined areas, the procedure is called focal ablation. Or if the affected tissues are larger areas with more complex rhythm disturbances, the doctor may perform a procedure called ablation remodeling. Both types of ablation restore normal electrical impulses and prevent an arrhythmia from happening. If the cause of the arrhythmia is in the ventricle, the doctor can do either focal ablation or ablation remodeling to treat more complex arrhythmias of the ventricle.
Okay. So, in the video what you have seen, in the video you have seen that a surgeon has to insert a catheter, right, in the heart, and then where the catheter is inserted they look at the electrical signal. So, where is the misfiring of the electrical signal, that is called electrical mapping, alright. If you have the heart chamber and if I insert a catheter, catheter is nothing but a tube, right. So, tube, and then at the tip of the tube you have electrodes which are recording electrodes to measure the electrical signal. Now, once you have the electrical signal they take the tube out and insert another tube, tube is a catheter. So, they insert another catheter, and then wherever the electrical signal was not correct, right, that particular region the surgeon will ablate. Now, ablation is nothing but heating, right. If you heat the tissue it will burn, if you burn the tissue it will not conduct, technical term ablation. If I use RF frequency, RF ablation, because I am using catheter, RF catheter ablation, right. And when a person ablates or when a surgeon ablates, right, he or she needs to understand how much force is applied on the heart tissue, because when you want to apply RF on the tissue you have to touch the tissue, right, you have to press the tissue and then you have to apply. So, how much force is applied? If the force is too much, then all other part which we do not need to ablate will get ablated. If the force is less, then the recurrence is higher, means a person would have a same episode after the surgery is done. Both cases are not good. So, how to treat a patient correctly? There is something called transmurality. Transmurality is where when you ablate the tissue it ablates completely, right, because anyway heart is also tissue wall, right. So, let us say this is the thickness of the wall, this is the thickness of the wall. If I am ablating from one side, how I am sure that the complete tissue is ablated, right. It may only ablate half, it may not reach this area, right. If I ablate from the front it may not reach back. So, if it does not reach back, that means the front is burnt but the back is still conducting. So, I need to make sure that the entire thickness of the tissue is burnt or ablated, and that is called transmurality. How to make sure that the surgery has resulted in transmurality, and how much force need to apply. So, that is why very easy is how to design a force sensor. It is a catheter contact force sensor that lot of people are working on, and I will show you two different ways. First is a very simple way of understanding or designing a 3D force sensor, 3D MEMS based force sensor we say. It cannot be used in actual ablation, but the next version in the same topic I will show it to you that can be actually used in ablation. Okay. You reach to second point only when you start working somewhere. So, that is how I will show it to you. So, if you see here on the slide, we will talk about the 3D MEMS based force sensor for catheter contact force. The sensor is nothing but a strain gauge on a flexible material. Let us see the process flow of this particular sensor. You start with a silicon wafer, and then you have a P dot PSS over PDMS. So, you coat the PDMS, you cure PDMS, on that you deposit or spin coat P dot PSS. PDMS is flexible material like I have discussed earlier. P dot PSS also I have discussed is a strain gauge, and then after you do that you can the silver is used so that to better adhesion of this particular material, which will help in the patterning process. Then you have to pattern this P dot PSS to form a strain gauge. You can see here. After you do that, so after you perform photolithography, you have to dip this wafer in silver etchant followed by P dot PSS etchant, and then you form the strain gauge. Strain gauge looks like this. Right, it is very simple process, single mask process. You guys now know how to fabricate a strain gauge with using lithography, right. Now, once you have this P dot PSS strain gauge, you need to attach a bump on this P dot PSS strain gauge along with gold pads. So, first is this contact pads that you can see here, we need to deposit gold and pattern it such that we have a ohmic contact, right, from the sensor, and then we have to attach a PDMS bump. So, how to create PDMS bump? For that you need to see this one, this particular process flow. You have a silicon wafer, and in silicon wafer if I create a pit, if I deposit or spin coat PDMS, cure it and peel it off, I will have a PDMS bump. Simple, right. Silicon wafer, silicon pit. How to create silicon pit? So, if I take a silicon wafer, I oxidize this silicon wafer, right, and then you create a window, using lithography, right. You can remove silicon dioxide using BHF, then you add silicon. If you add silicon, what will happen? Silicon will get etched, right. What will happen? Silicon will get etched like this. Okay. This is what is creating of a pit. Now, if you load PDMS, you can remove silicon dioxide, right. You can remove silicon dioxide by dipping this wafer in BHF, and if you load PDMS on this, and if I strip this off, I have cured PDMS, this is PDMS, I cure it and strip it off, what will I have? I will have my PDMS like this. If I slice the PDMS, then what will I have? I have a PDMS bump, right. This is what is shown here, right. So, very simple process, is not it. Now, this PDMS bump we will stick it on our PDMS bump, we will stick it on our strain gauge which is fabricated using P dot PSS. After this you can strip off the PDMS substrate from the silicon and you will have a flexible force sensor. Easy, that is what is flexible force sensor. Now once you have flexible force sensor, what you will do, you will take a bead, is a cube, small cube like this, right, and on each side of this cube you will stick one PDMS. So there are how many slides? Slide 1, 2, 3, 4, 5 and 6, right. One slide you will not use it because you have to attach that sixth slide to the catheter tip, alright. So you will only attach 5 sensors on 5 sides of the cube, and this is shown in this particular schematic diagram, that you have sensor 1, sensor 2, 3, 4, 5 on all the sides you have sensors. You can do very quick COMSOL simulation where how much force you apply and what is the stress factor on the strain gauge, right. So if I have this now if I have the sensors attached on this particular cube, then I will have how many contacts? 10 contacts, right, because each strain gauge will have 2 contacts. All these sensor contacts can be brought out from within the catheter. Now once you have that, first is how you want to understand that, or how you know that what is the change in the sensor values for certain force. So for that what we do is we take a commercial force sensor attached to a micro manipulator and press it on the particular fabricated sensor. When you press it on sensor, you will see that on applying of compression force, what is sensor output voltage. Now instead of measuring resistance, we can always use a potential divider to see what is the change in the voltage, or if you use a Wheatstone bridge, accordingly you can see the change in voltage. So when you apply a force, known force, then you will see what is the output voltage. From that you will you can get the data for the fabricated sensor, and from the data you can understand that if there is a certain voltage change, that means that it is corresponding to that particular compression force, right. So this is very important experiment that you need to perform whenever you fabricate any sensor. You have to take a commercial sensors and perform the calibration part, okay. This is called calibration. Alright. Now if I want to apply a force onto a tissue, if I go for a tissue, before that I have to go for a phantom tissue. Phantom tissue is not real tissue, and phantom tissue can be fabricated with the help of gelatin. So if I take a box like a metal box in which I can have a gelatin, right, and I take a force sensor which is a commercial force sensor, right, versus the catheter, and I press it on the gelatin, then I will see that what is the calculated contact force sensor output and calculated contact force versus measured contact force. Now you can very clearly see that this is extremely linear, and that is a good thing about a sensor. Sensor should show a linear change in the output response for different forces. For example, if I apply 5 grams of force and I remove that force, what is the response time? Same thing goes for 40 grams of force, 60 grams of force. Then you can see that this sensor can measure anywhere from 5 grams to 60 grams, and like I said, very important problem is how much force you are applying. The optimum force is somewhere around 35 grams to 40 grams on the heart. Alright. So when the as you have seen, the catheter is ablating a heart tissue, that ablation force should not be more than 35 to 40 grams. This is optimized force. Okay. Now when you actually insert the catheter inside the heart, right, then it has to pass through the blood vessels, and that is why how the sensor would act when there is a force of a liquid media or medium on the sensor. And for that, what this experiment shows is that if you have the catheter and you have several sensors, sensor 1, 2 and then water, and if I move the sensor in x direction or y direction or z direction, the corresponding sensors which are attached to the catheter will change its property, right. and the what we have given notations are this is, let us say, fx1, this is fy1, and this is fz1. Same day if you take a sensor 2, then fx2, fy2 and fz2. So, when I perform these experiments, I can see that based on where the force is acting, I can see that particular the values are different. For example, fz1 and fy2, you can see here it is different, right. When I apply force in this direction, fz1 is different than fy2, same thing fz2 is different than fx1. So, you can very clearly understand that you can delineate the force that is applied on a certain part, or if whether it is normal force or whether it is shear force, you can delineate, and that is very important. So, learning from this all experiments, what now we have thought is how we can design an actual catheter that can be used for ablation. This is a maneuvering system for that particular catheter. Maneuvering system is how to move the catheter in the real world. There is a knob, there is a top cover, there are thread bolts. Again, you can design this either with 3D printing, or you can use other manufacturing techniques. There is a guide pulley, SS tendon, and then there is a vibration motor for haptic feedback. So, let me come back to haptic feedback. I told you that there is a force sensor which is required at the tip of the catheter, but at the same time a very important problem that is there, or gap that is there in the current catheters, are that none of the catheters has a haptic feedback. Haptic feedback means the feeling of force, right. So, how much force a surgeon is applying on the heart, he or she only can see on the display, but cannot feel the force. So, how about we design a catheter in which you can not only see the force, but also you can see the force, and that is called your haptic feedback, and that is why we will convert the force values to the haptic feedback. There is a bottom cover, and then there is a thread holder bottom. In between we have also used the nitinol spine. Nitinol is a smart material, is extensively used in the new catheters, and then the jacket is consist of the polyurethane, and this is the jacket we are talking about here, right. So, that the catheter can move or maneuver, and this is the catheter tip. If you see the tip, there is a ablation electrode, then there is a elastic material, there is a sensor, PCB, and then pogo connectors, followed by the alignment modules. Alright, this is the sensor design, and if I go further, then you will see that the blown up diagram of this particular catheter tip. We are only talking about tip which is right over here. Okay, that is it. So, if I talk about the catheter tip, then you can see that the tip is of ablation electrode which is of metal, and then sensor is right over here. So, we are interested in designing this sensor as well. If you lock it together, it looks like this, and then you can see here there are some holes. This is for the irrigation type of catheters. Irrigation type of catheters are the catheters in which you use the saline media to make a way through the blood medium. Now, based on this, we can design several kind of force sensors. The force sensor that I am showing it to you here is the design 1, right, and then we have design 2, and then we have design 3, right. So, design 1 is that you have the bridges here, right. Design 2, you have holes in these bridges here, and design 3, you have a meander shape or a coil shaped sensors. Now, actually the sensor that we will be using is a diffusion based piezoresistive material, and the diffusion occurs right at the tip of this particular bridge, like this, and then there are 2 here. I will show to you how exactly we have designed it, but my point is we have taken this bridge structure and then made a hole in that, and then we have used this serpentine structure just to improve the sensitivity. The dimensions are given here, which is not really important for you, but the point is, as you can see here, we have 4 strain gauges, 1, 2, 3 and 4. If I have a magnified version of that, then you can see very clearly the strain gauge which are 4 in number here are there. So, two they will balance out the another two, and we can use the circuit with Wheatstone bridge. We have tried different designs, and this is actually fabricated sensors with us, right. One with directly there is no hole in the bridge, second one is there are two holes, and third one is with the serpentine structure, right. So, this is how the sensor looks like. Now, if you recall your earlier discussion or earlier lecture in which you were taught COMSOL multiphysics simulation, using the same COMSOL multiphysics you can understand that what can be the optimized design for my force sensor. For example, if I want to know what is the displacement versus bridge length for various bridge thickness, then I can give that values and I can get that total displacement versus bridge length. From that I will understand what should be my optimized bridge length for the given displacement, alright. Same way, if I apply a normal force or apply shear force, how the sensor would behave, that is what is given here. You see here that when I apply normal force, almost all these x up, x down, y up, y left, y right, right, everything is kind of increasing linearly, right. So, stress versus normal force on all bridges, as you can see here, it is very easy to identify if you once you know COMSOL. And here we have shown the displacement map for various bridge thickness at 0.8 Newton normal force on the catheter tip, that how each sensor would behave, and you can clearly see that the stress is right in the on the bridge. Because of the stress or strain, the resistance would change, because these are all piezo resistors, right, these are piezo resistors, alright. So, if I let me show it to you very quickly how can you diffuse one single piezo resistor, and then you can take it forward from there. So, I will just show it to you. If you have an oxidized silicon wafer, alright, oxidized silicon wafer, then if I want to, let us say this is N type and this is my silicon dioxide, right. What I will do is I will open a window, I am just showing you quickly, okay. So, that you understand, I will open a window like this in silicon dioxide, and then I will spin coat my boron. Either spin coat, there are different ways of diffusing boron or impurities into silicon wafer. One is a solid way, then another one is liquid, and third one is with gaseous phase. We will use a liquid phase just for this particular class, and in that you can spin coat this boron on this particular silicon dioxide or oxidized silicon wafer with a window that you can see. Now, after this you have to, so when you discuss about diffusion, diffusion has two process, one is called pre-deposition, second is called drive in. So, you have to first pre-deposit, so you have to anneal this or heat this around 400 degree centigrade, 400 to 500 degree centigrade, okay. Once you do that, this layer will start like this, just little bit into the silicon wafer, alright. Now, if I heat this further, which is called drive in, at a higher temperature, or let us say around 900 degree centigrade to 1100 degree centigrade, right, this will start driving in and form a diffusion layer. After that you can dip this wafer in SiO2 etchant, and this everything will come out. So, now what you have is, you have a P material, a N material. If I take a contact from here, and if I take contact from here, it becomes your PN diode, right. But we are not talking about PN diode, we are talking about diffusion. So, now we have this P types of this was a boron doped in N type wafer. If you open a window in this particular fashion, then you can have a strain gauge, this is a cross section of that. So, now once you have four of those, how can you connect it? You can connect it with the metal deposition, and then we will also see if possible, if the time permits, that how the process occurs. So, I will go to the next study right after this. So, that is why I was showing it to you how diffusion occurs, because when there is a force on this particular bridges, there is a change in the strain which causes the change in the resistance. Now, instead of normal force, if I have angular forces, then how my sensor would behave? I have all the simulation data here, that which sensor would change, or which side of the bridge would have more stress compared to the with respect to each other, and here also you can have stress versus angular force on all the bridges. You can see very clearly that you can delineate those parameters. If I see the simulation results for the piezoresistor length. Now, first one was about the bridge, right? What is the bridge thickness, bridge length. Second one is what is the piezoresistive thickness and piezoresistive length and a width. So, for the line width of 5 microns and for line width of 60 microns, how the resistance versus normal force changes for a given piezoresistor. This is all simulation results that we have done, and you can see. And then once you have this all the data, what you can do is you have to use this catheter onto the heart, and which heart you can use? Pig heart, because pig heart is very close to a human heart, and in that pig heart you can use this catheter and get all the data from the catheter, right, whether it is the force sensing data or you want to ablate that tissue, you can use the pig heart. Now, to get the pig heart, again you have to get the ethical clearance, and for ethical clearance you have to apply to Institute Ethical Committee. So, we have got the ethical clearance, and then we also got the biosafety approval clearance. So, to use the pig heart in our laboratory. All right. So, this is how the cardiac ablation will work. I would discuss other topics in the next module, right. Till then, you take care. If you have any questions, feel free to ask me. It is not so easy to grab this kind of applications. These are little bit towards advanced research or application of your sensors for healthcare technologies with a little bit of advanced side. Okay. So, you may be confused in some of these slides, and if you are, feel free to ask me questions. Okay. But if you again go in depth, it is nothing but a force sensor that we are developing with the help of strain gauge, to make it very simpler. Whatever force sensing data we get, if we can change it to the vibration mode, right, then the surgeon will also feel how much force he is applying or she is applying on the heart. That is the idea, and that is why I said smart catheter instead of just catheter. Right. So, I will see you in the next lecture. Till then, you take care.